Hi there, this is Heath. This is the second part of our introduction to eigenvalues and eigenvectors. We're going to review an eigenvector of a square matrix A is a non-zero vector whose direction is unchanged when we multiply that vector by A. That means AX is an exact multiple of X. For historical reasons, we used the Greek letter lambda to indicate this multiple. And so the definition in the book is that X is an eigenvector if A times X equals lambda times X for some value lambda. This value lambda is called the eigenvalue. Every eigenvector has an eigenvalue. And only square matrices have these things. So let's try a couple of examples. If this is my matrix A, we want to show that 3, 8 is an eigenvector of A. So we're going to figure out what happens when we multiply 18, negative 3, 16, 4 times 3, 8. We've got to apply the row column rule. So we get 3 times the first column and 8 times the second column. Three times 18 is 54. 3 times 16 is 48. 8 times negative 3 is negative 24. And 8 times 4 is 32. 54 plus negative 24 is 30. And 48 plus 32 is 80. And so this vector that we finished with is exactly 10 times bigger than the vector we started out with. And so our eigenvalue is 10. Here's a 3 by 3 matrix, and we know that lambda equals 3 is an eigenvalue. That means when I multiply this matrix times some vector, the answer will be 3x, 3y, 3z. That there is some vector that gets 3 times bigger when we multiply these together. But I don't know what this vector is yet. So let's column row rule this. X times negative 37, 10, and 45, plus y times 40, negative 7, and negative 45, and z times negative 40, 10, and positive 48. And this will equal to 3x, 3y, 3z. If I look at the top row then says negative 37x plus 40y minus 40z is equal to 3x. The middle row says 10x minus 7y plus 10z equals 3y. And the bottom row says 45x minus 45y plus 48z equals 3z. What I'm going to do is take all three of these terms on the right-hand side and bring them over to the left side of the equations. And so now I have negative 40x, because I've subtracted 3x, plus 40y, minus 40z is equal to 0. And then 10x, when I subtract 3y, this becomes negative 10y, plus 10z is equal to 0. And then 45x minus 45y. When I subtract 3z, this is plus 45z is equal to 0. And we can solve this with an augmented matrix, negative 40, positive 40, negative 40, 0. 10, negative 10, 10, 0, 45, negative 45, 45, 0. If I divide this row by 40, by negative 40, and divide this row by 10, and divide this row by 45, then all three rows become 1, negative 1, positive 1, 0. And I can use the row on the top to cancel the other two rows. Here is my bound variable, and these two variables are free. And so my solution set is that x is equal to y minus z, and then y is equal to y, and z is equal to z. And so y is being multiplied by the vector 1, 1, 0, and z is being multiplied by the vector negative 1, 0, positive 1. And these two vectors are linearly independent, and they are the eigenvectors for this matrix. All right. I want to talk about what's happened here, though. This is a pretty messy slide, but some of the big picture things here is that we had this system of equations here that when we brought these terms over to the left side of the equation, the only terms that changed on the left side were the diagonal terms. We subtracted the eigenvalue lambda from each number on the diagonal. And then what we were left with all zeros on the right-hand side, but that's the hallmark of a homogeneous system. And it's a homogeneous system that had free variables. So let me summarize those three important points here. We subtracted lambda from the diagonal, we ended up with a homogeneous system, and the homogeneous system had free variables in it. So if I had some matrix in general, and I have some eigenvector of A, then the matrix times a vector is an exact multiple of the vector. And when we multiply this out, we have this system of equations, and the lambda x will combine with ax, and lambda y will combine with ey, and lambda z will combine with iz. And again, these are the diagonal entries that will change. A, E, and I become A minus lambda, E minus lambda, and I minus lambda. They were A, E, and I. They are now A minus lambda, E minus lambda, and I minus lambda. When we do that, we have a homogeneous system. So if we modify the matrix by subtracting lambda from the diagonal values and then form a homogeneous system, then V, the eigenvector that we started out with, is a solution. But we know even more than this. V is not 0 because eigenvalues are not allowed to be 0. Eigenvectors, sorry. Eigenvectors are not allowed to be 0. And that means a homogeneous system has to have more than one solution. It will have the trivial solution, the origin, and it will have V. And as soon as you have two solutions, you have an infinite number of solutions. And that means the solution has to have a free variable. And that was the third thing that I mentioned a moment ago. What does that tell us about the determinant of this matrix now that we've modified it by on a diagonal? That if the matrix has a free column in it, then the determinant has to equal 0. I'll talk about this notation in just a moment. So to find the eigenvalues for a square matrix, we modify the matrix by subtracting lambda from the diagonal values, then make the system homogeneous. And then take the determinant and make the determinant also equal to 0. This is a formal notation for the modification we're talking about. If I start with the matrix A, minus lambda times I is the name for the identity matrix. We've seen that before. It was on homework 6. But when I multiply lambda times I just get lambdas in the diagonal positions, and I end up with A minus lambda, B, C, D, E minus lambda, F, G, H, I minus lambda. And so anytime you see this notation, it means take the matrix A and subtract lambda from the diagonal. And that's how we get the eigenvalues for the matrix. You ready to try an example? Let's go. This is example 124. I want to find the eigenvalues for this matrix. So the first thing I'm going to do is subtract lambda from the diagonal. And that gives me the matrix negative lambda, 1, 2, 1 minus lambda. Then the second thing I'm going to do is take the determinant of this. That's going to be negative lambda times 1 minus lambda minus 2. Multiply these two together and then multiply these together and subtract. If I FOIL this out, this is lambda squared. Negative lambda times negative lambda is lambda squared. Negative lambda times 1 is minus lambda, minus 2. And then the third thing I'm going to do is set this determinant equal to 0. And this factors into lambda plus 1 and lambda minus 2. And so my eigenvalues are negative 1 and positive 2. That's example 124. Same matrix, this is example 125, but this time we want to find the eigenvectors. We saw from the last example that the eigenvalues were negative 1 and positive 2. So what we're going to have to do to find the eigenvectors, We have to do this procedure twice for each of the eigenvalues. So unfortunately, we have to do this process twice. First thing I'm going to do is subtract the eigenvalue from the diagonal. So we'll do lambda equals -1 first. When I subtract -1 from the diagonal, zero minus -1 is 1, and 1 minus -1 is 2. Turn this into a homogeneous system by augmenting with zeros. And then row reduce. Well, I've got to row reduce by taking row 2 minus 2 row 1, and we get 1, 1, 0, 0, 0, 0. We have a free variable, and that's what we were expecting. If we don't get a free variable, we have done something wrong. But we did get a free variable here. And so my system of equations is that x1 is equal to -x2, and x2 is equal to x2. And so x2 is equal to, or x2 times -1, 1 is my solution set. And so -1, +1 is one of the eigenvectors. And then we have to do this process again. Start with 0, 1, 2, 1. Subtract 2 from the diagonal. So now I have -2, 1, 2, 1 minus 2 is -1. Take this matrix and make it into a homogeneous system. And we have -2, 1, 0, 2, -1, 0. And when we row reduce this, I'll divide the top row by -2. I get 1, -1/2, 0. And the top row and the bottom obviously cancel. And again, I have a free variable in my system. I'm always supposed to have a free variable. And this system says that x1 is equal to 1/2 x2, and x2 is equal to itself, which is x2 times the vector 1/2, 1. And so 1/2, 1 is another eigenvector. And now we have both eigenvectors for this matrix. So in example 124, we found the eigenvalues. In example 125, we found the eigenvectors. Let's try one more example. Let's use these examples to compute 0, 1, 2, 1 raised to the 10th power times 5, 1. So from the previous examples, we saw that the eigenvalues were -1 and 2, and that -1, 1 was an eigenvector, and 1/2, 1 was an eigenvector. What I would like to do is find a combination of the eigenvectors to equal 5, 1. So can I write 5, 1 as a combination of eigenvectors? And we can do that by solving this system here. Find a combination of these columns that adds up to 5, 1. If I take row 2 plus row 1, this could be 0, 3 has 6, negative 1, 1/2, 5. Take negative row 1. Get rid of that 3 halves. 2/3 of row 2 gives me 0, 1, 4, 1, negative 1/2, negative 5. And then finally, row 1 plus 1/2 row 2 gives me 1, 0, negative 3, 0, 1, 4. So if we did this right, negative 3 of these vectors plus 4 of these vectors is equal to 5, 1. Does that check? In the top row, we get positive 3 plus positive 2 equals 5. In the bottom row, we get negative 3 plus positive 4, and that equals 1. So that checks. Now that we have this combination, I'm going to replace the 5, 1 in the equation with this combination. 0, 1, 2, 1 to the 10th power times negative 3 times negative 1, 1 plus 4 times 1/2, 1. But I know what happens when I multiply this matrix by negative 1, 1. It scales by a factor of negative 1. And so in the next step, I'm going to replace this matrix to a power with the eigenvalue to a power. This is the same thing as negative 3 times negative 1 to the 10th power times negative 1, 1. Plus, in this example, 4 times 2 to the 10th power times 1/2, 1. All right. So negative 1 to the 10th power is positive 1. Positive 1 times negative 3 is negative 3. And negative 3 times negative 1, 1 is positive 3, negative 3. Over here, the numbers get a little bit bigger. 2 to the 10th is 1,024. And then 4 times 2 to the 10th is 4,096. 4,096 times 1/2 is 2,048, and 4,096 times 1 is 4,096. When we add these together, we get the answer we wanted. The top row is 2,051, and the bottom row is 4,093. And we computed this without ever having to multiply this matrix out 10 times. That's kind of a powerful thing that we can do with eigenvalues and eigenvectors is that they allow us to raise a matrix to a power more efficiently. Next week, we'll look at some examples of how that might be useful. Y'all have a great weekend. Take care.